right, hello everyone. Today we've got a linear algebra problem, and we have the following. We have a set which contains the vectors v1, comma, v2, comma, v3, and we're going to let this set be a set that's linearly independent. Okay. It's a set of linear independent vectors, and these vectors all belong to a vector space V. And what we're going to do here is we want to prove that the set, which is made up of the vectors v1 plus v2, comma, 2v2 minus v1, comma, v3 plus 4v1, is also linear independent in V. All right, so the first thing I'd like to start off with is going over what the definition of linearly independent is, or linearly independent set of vectors. There's a couple definitions out there. Just to let you know, I'm going to use this one. So a set of vectors v1, v2, comma, all the way up to vn, such that vi is in V, and all I'm saying here is that all your vectors are elements, that's what that little kind of E symbol means, of V, meaning they're members of this vector space V, where V is a vector space, to be linear independent if you take the linear combination of these vectors, so C1v1 plus C2v2 plus CNVN, you set that equal to 0. This only equals 0 if all the constants equals, all the scalars equal 0. I'm sorry, scalars C1, C2, Cn. And here I just made a side note that all your scalars are members of the real numbers. It could also be members of the complex, but we're just working with the real numbers today. All right, so when I'm writing out a proof, I like to write out what I need to show a lot of the time. There's a few techniques out there for writing proofs out. There is direct proofs, that's what we're going to go over today, proof by contradiction, induction, etc. But just, yeah, if you're studying proofs, this is a proof, direct proof, okay? And often with a direct proof, we'd like to write down what I need to show. And in this case, I'd like to show the following. Using that definition, that if you take this linear combination of vectors C1 times V1 plus V2 plus C2 times 2v2 minus v1 plus c3 times v3 plus 4v1, all set that equal to 0, then all these scalars c1, c2, c3 are equal to 0. Okay, so that's what I like to prove. Now, what I like to do also is use that hypothesis somewhere when you're working with a direct proof. So the hypothesis here is that the set v1, v2, v3 is a set of linear independent vectors. Okay. Now, how do I go about doing that? Well, that's where sometimes it takes a little bit of, sometimes, yeah, I'd say it's a bit of a creative process in some cases, or in some cases it's just a matter of doing like algebra like it is here. What I mean by that is I'm going to take the statement that I have up here, and I'm going to just distribute the C's, okay? So C1v1 plus C1v2 plus 2C2 v2 minus c2 v1 plus c3 v3 plus 4c3 v1. Okay. And because the hypothesis said that your vectors are linearly independent, I'd like to get some definition, something with like the v1s, v2s, and v3s, like a statement like what I had up here somehow with v1, v2, v3, because that's what the hypothesis in a way is stating, is that if you take if you take the linear combination of the v1, v2, and v3, set it equal to 0, then all the c's equal to 0. So I'll write that down in so many ways. So the way I'm going to do that is I'm going to go ahead and combine every term in the sense of I'm going to combine all the v1s. So all the v1s would be like right here. All the v2s, that's next. So that would be c1 v2 plus 2c2 v2, so that's that. And then all the v3s, which looks like there's just one here. And set it equal to 0. And now I'm going to go ahead and factor out the v1s, the v2s, etc. So c1 minus C2 plus 4C3 V1 plus C1 plus 2C2 V2 plus just C3 V3 equals 0. Okay, so we did that, and we're allowed to do that because we have properties of vector spaces that let us like factors and such. Now, here's where I'm going to use that hypothesis. Because V1, V2, and V3 are linearly independent, then we have to have that the constants in front of each of these have to equal 0. So I'd have to have that C1 minus C2 plus 4C3 equals 0, C1 plus 2C2 equals 0, and then C3 equals 0. And what can you do with this? Well, you can actually set this up as a system of equations in a matrix. Sorry, this system, put it into a matrix. 2, 0, 0, 0, 1, and row reduce this, okay? And if you went ahead and row reduce this expression, you would get 1, 1, 1, 0, 0, 0, 0, 0, 0, and a bunch of zeros, okay, here. And that would imply, so yeah, so it's going to take a couple steps here. I'm not going to go over that because it's going to take too much time here. But you would get this statement, and you would get that from that, sorry, that statement being that augmented matrix, that each of the C's equals 0, okay? And that's what we were heading for. So that's why you study a lot of the things that you with matrices in the beginning, is because those are going to help you to prove results like we did here. We use the mechanics that we learned from matrices to help us prove that the constants were equal to 0, okay? So that's somewhat of a typical proof with a linear algebra problem, where you're asked to show something is linear independent and you have a system of equations and you need to solve it. A couple of things you could have also done, you could have also set this up as that system of equations that appear as a product of matrices as such. So this is like reminiscent to when you saw like AX equals B, and we knew that if A was invertible, then actually let me switch the B to 0. If A was invertible, then you would only have the homogeneous solution, or all the C's equal to 0, and that's going to happen here actually. If you take the determinant of A, the determinant of A would equal, looks like it's going to equal like 3 or something. So only the homogeneous solution exists. So yeah, so there's a couple ways of actually proving the result for this problem in terms of the method. You can use row reduction, or you can look at, rewrite this as a matrix multiplication of the system and check the determinant of A and see if it's equal to 0 or not. And there you go. All right. Well, thank you for your time. Hope this helps.